Hello, today let's take a look at the basics of CUDA programming. So when you speak of CUDA programming, you're talking of C and C++. After all, the CUDA is just a C or C++ with added keywords. A CUDA source file ends with a CU extension, and of course, the usual C++ ends with a C or CPP extension. Usually, the entry point of all CUDA program starts with a C or C++ code. The C++ code compiles into a binary that is gets executed by the CPU, or the term is host, CPU or the host. So all of this gets compiled as a binary by GCC and gets executed by the CPU. So it will call this function here, do transpose, and then if we go here, the do transpose, this is a stub. This is still, even though this whole content here is inside the helper, that's CU, okay? But this part here still belongs to the CPU code. So this gets executed by the host or the CPU. But when it calls the function transpose here, and the way that it makes that call is through this like this. So it passes a parameter here, and in addition it passes some additional parameter in this bracketed weird triple bracket enclosure. So transpose and this one transpose. This function implementation I selected here, on the other hand, gets executed in the GPU. And because of the nature of the problem that we're trying to solve here, which is operating on the elements of a vector or a matrix, this part here will get, looks like a reentrant like 100 times entered here, each time with a different value of black dx or y, and so they will not interfere with each other, and the output will be written to a separate cell while the rest of the elements of the vector are computed similarly in a different thread or a core of the GPU. So like hundreds of these doing together, computing them in parallel, but the CPU here, while invoking that call, has to wait for the GPU to finish. And after that, it will do some basic checks if it succeeded, and then it will return the result of the transpose operation. So that is how speed or the massively parallel uh, facility of CUDA cores speeds up execution of vector. If the problem does not contain vector or matrix, there's it cannot it's not good for CUDA. Or this it's not for CUDA programming. So it is for a very special class of problems that uses or involves matrix or vectors, which are inherently data structures that can be solved in parallel. So let us go to the makefile. Let's take a look at the makefile, how to build this thing. The CUDA source file helper CU is built uh, using the NVCC compiler driver from CUDA toolkit. Not shown here. There's a invocation of the GCC hiding here, and together the NVCC and the GCC produce helper.o. And there's also an option you pass through gene code, which must be set correctly to match the GPU architecture. So if you're using a different older CUDA, so it will be, there's a corresponding value of this SM or symmetric multiprocessing, an integer. And when this .o is produced, the binary, it will get linked into the main driver of the application, which is G++. And then these are the usual include and linker. And there's also a runtime CUDA. So let's try to build this. Make SM89. 89 corresponds to the value of my GPU, which is, let me, NVIDIA SMI, which is GeForce 4070. So if this 89 here do not correspond to your GPU, then your program will not run. So this is so low level that you need to tell it the correct value so that the gene code and option of NBCC shall produce the correct binary. Okay, so enter. So now we produce one binary up. This one binary is a fusion of the host code and the device code. It is a fusion of a binary code produced by G++ and a binary code produced by NVCC. But the entry point still is the CPU code. So the CPU code, it starts with the CPU code and then trickling down to invocation of the CUDA call kernel, and that part gets delegated to GPU. The CPU will wait, and after waiting, then the result is gathered back, and then the output is printed. So let us try to run this. It's very fast. I did not print the entire matrix. I just print the first three elements, but I think this matrix is 5 by 5, so I just printed. Let us try to. Yep, I just printed the first three elements in the transpose of this matrix vector. But there are many parts that are arranged in order to make this happen. So first, you cannot just install the CUDA toolkit that is responsible for the NVCC and then pair it with any C++ or C compiler. You cannot do that, as every NVCC has to be compatible with the corresponding GCC or G++. So there is a pair of these two compilers. They need to be paired in order to work together. So you cannot just throw an NVCC to any compiler and expect it to work. No. These two compilers, the host compiler and the device compiler, or the CPU compiler and the GPU compiler, has to understand each other because after all, um, they produce one binary that is that orchestrates the execution of the thing. There's also a library, the runtime, but there's also an operating system kernel that is responsible here. So if you check in the Linux kernel ls mode, you can see that these kernel Linux kernel drivers have been loaded in the Linux. Okay, and there could be many reasons that you could not make it work. For example, if your BIOS has a secure boot enabled and you did not properly install the CUDA driver with proper registering it through a manage a machine owner key, which is an entirely different sequence to introduce the driver using cryptographic methods, or if you recompile the kernel and the existing key is now no longer valid, then suddenly you will not be able to run this. Without the driver loaded in the kernel, you cannot run CUDA. You can compile the binary, you can produce this binary, but you cannot run it. So the best evidence that your system is properly set up is simply to run NVIDIA SMI, which is a built-in utility And if you get a results from this command, then that is a good sign that your system is ready for CUDA development. Otherwise, if running NVIDIA SMI will give an error like could not talk to the driver or not matching CUDA version, then you need to figure it out because it's your environment is not set up. And of all the Linux distros out there, I find Ubuntu to be the most well supported in terms of NVIDIA CUDA ecosystem. And the next would be Fedora, but I haven't explored it much. But I compared it initially very quickly, and Ubuntu is the best, the easiest, well integrated with NVIDIA CUDA. And if ever you have problems with um, breaking of the managed machine owner key, cryptographic signing of the NVIDIA driver, or the kernel is recompiled, the most developers disable the secure boot of their BIOS UEFI. In fact, I disabled mine here to check if yours is disabled or not. You just type mo key SB state or secure boot state, and it's disabled. Okay. If you will have it enabled, then there's an additional step you need to do to sign the NVIDIA NVIDIA driver. And when you reboot the Ubuntu, you will see a blue screen, and there's a menu called mock register or mock enroll. You type a password. It's uh, it's a flaw on its own, but to go away with all of this registration, you just disable secure boot, and then you are on your way to CUDA development. That is that is all. Thank you.